Hello, this is Mrs. Sargent, and this is lesson 3.1, Light and the Bohr model. So normally, when we think about light, we think about a light bulb, and that's the white light. But if you look at it through a prism, it separates it out into different colors of light. And we can see here the amount of energy associated with that light, the wavelength, and the speed. Notice that the speed is the same for all of the different colors of light, which is 3.00 times 10 to the 8th meters per second. So no matter what color of light it is, it's all going to travel at the same speed. And then if we look here at the photon energy, violets have the largest number, so that's going to be the color of light with the highest energy. And then reds have the lowest number, so that's going to be the colors of light with the lowest energy. And then if you look at wavelength, for the longest wavelength, reds have the longest wavelength because they have the largest number. And for the shortest wavelength, that is going to be our violets. So shorter wavelengths have more energy. And longer wavelengths have less energy. So you'll need to know the different colors of light and how their wavelength and energy compare. I like to think about it like this, that during the summer, the temperature is warm. So out of all of our colors here, reds are our warmest colors. During the summer, we have a lot of daylight, so our days are long. So the wavelength for our warmer colors is also long. And during the summer, like, I don't have as much going on, so I don't have to be as high paced and high energy all throughout, so I can have lower amount of energy. During the winter, it's cold, and our cooler colors is the violets. During the winter, the days are shorter. There's not a lot of daylight, and so we have shorter wavelengths for our cooler colors. And then during the winter, we're in the middle of the school year, and so have lots going on and need to be high energy all of the time. So that's kind of how I remember which colors go with what wavelength and what amount of energy. So in class, we looked at a hydrogen gas emission tube, and we drew these spectral lines in for what we saw through the viewfinder. The viewfinder just kind of separated it out by the colors of light. So we start with violet over here on the far left, and then we have a blue, and then we have a really thin green line almost in the middle, and then we have a thick red line on the far right. And then if you want to go in and label the wavelength in here, we have 400 over here on the far left, 400 nanometers. And then about in the middle, we have 500 nanometers. And then over here on the far right, we have 700 nanometers. So which color of light corresponds to the shortest wavelength? Well, that would be our violets, which is the same as what we saw on the chart on the first page, at the top of the page. The longest wavelength would be our reds. The color with the most energy, because it has a shorter wavelength, would be our violets. And then least energy, since it has a longer wavelength, would be our reds. And then we also looked at a mercury gas discharge tube. And we saw some of the same colors, but we didn't see the exact same colors. So they are not exactly the same, but there are some similarities. So here we have the spectral lines for 5 different elements. We have hydrogen, sodium, helium, neon, and mercury. And we have this statement: the spectral lines for atoms are like fingerprints for humans. So how do the spectral lines for the gas discharge tubes support this? Well, if you look at these, none of the spectral lines are exactly the same for any of the different elements. And just like you do not have the same fingerprints as anybody else, neither are the spectral lines going to be the same for other elements. So just like we use the Bohr model to look at the atomic structure, we're also going to use the Bohr model to look at electron transitions. So electrons are negative, protons are positive. Opposite charges are going to attract each other. And as an electron gets closer to the nucleus, the attraction to the nucleus is going to get stronger. Electrons orbiting the nucleus at fixed orbitals. That's how Bohr had his model set up. Electrons absorb energy when they go from lower energy levels, which is the ground state, to higher energy levels, which is the excited state. So just like you need energy to be able to climb a set of stairs, electrons need to absorb energy in order to go from ground state to a higher energy state. And then energy is released as electrons return to their lower energy levels, and the energy is in the form of light. So we have these 4 different diagrams, and each shows an electron transition. So we're going to look here at where the arrow starts. That's going to show where our electron is starting. So here we're at n equals 6, and it's going to n equals 2. In B, the arrow starts at n equals 5, and it is going to n equals 2. In C, we start at n equals 4, and it goes to n equals 2. And then in D, we start at n equals 3, and it goes to n equals 2. So our longest wavelength is here in D. And then our shortest wavelength is in A. C is a little bit longer than B, so this is going to be our mid to long wavelength. And then B is a little bit shorter, so this is going to be our short to mid wavelength. So when we looked at our hydrogen gas discharge tube and we looked at the spectral lines, we had 4 different colors. And remember, the purple or the violet had the shortest wavelength. So A is violet. And so then you can color this line to show that violet light is being emitted through this electron transition. And then red had the longest wavelength. So we can color code that to show that red light would be emitted here. And then we had blue and green left. So our blue light is going to be emitted with the short to mid wavelength. And then our green is going to be the light that is emitted with our mid to long wavelength. So which one of these electron transitions involves the most energy? That would be A, the n equals 6 to n equals 2. It releases violet light. Because it has a short wavelength and high energy. the electron has to go through many energy levels. So that's another reason that we know that there's going to be a lot of energy involved with that. Just like you expend more energy going from the sixth floor of a building down to the ground floor, you would expend more energy than someone that goes from the second floor of the building down to the ground floor. So why can't a single atom of hydrogen produce all four hydrogen spectral lines simultaneously? Well, you can't be in two places at once. A hydrogen atom has one electron. So it can only go through one transition at a time. So then how can all four colors from a hydrogen gas discharge tube be present at one time? The gas discharge tubes contain several atoms. And each atom of hydrogen can go through a different transition. So that's it for today's lesson. You have practice on the next page. Make sure you take a look at that and feel free to come in and ask questions if you need help. Thanks for stopping by. Have a great day.